I posted a bit of a study sheet for exam 3. Mechanisms you have to know. Well, actually, I didn't put in mechanisms you have to know. If I've done a mechanism in class and it's not on the excluded list, you're expected to know it. But that's going to be all the radical mechanisms. Quite a few of the mechanisms from 8 and 9. We'll pretty much finish new material today. We'll do some stuff on Thursday. What else is there? So the exam is a week from today, and it'll be in the labs in Salem. All right. So, would you guys prefer to take the exams in the lab or here?
Here.
No strong preference.
Here.
Let me look into. I mean, we are. I think we're over there. But I could just like stay outside. We're capped at a certain number. All right. So chapter 9, alkynes is where we are. Most of these reactions, like I've been saying, most of these reactions will do. The alkyne is going to do pretty much what alkenes do. So one of the 2 pi bonds is going to be a nucleophile, and then the only change is going to come that the product you get out of that is going to have an alkene still. All right. So we use one equivalent of HBr here. We'll do a Markovnikov. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We'll do a Markovnikov addition of HBr. Get a vinyl bromide. The way this works out, like I said when I talked about how electron-rich things are, how electron-poor things are, the halogens, because they're electronegative, tend to be electron withdrawing, right? So the vinyl bromide, the bromide on this alkene slows, it makes it a less basic pair of electrons than the alkyne by itself. So you can't actually stop this reaction at one addition. Of course, if you add in, right, if there's a carbon here and the cations would be roughly the same, both be secondary, you get both sides. And then obviously if you do one more equivalent, you can make this, you can add a second one, it's just slower. You get the general bromides. All right. Same thing is true for Br2. It's a little more complex. Right. Anti-addition of the 2 bromides, you would expect you'd get trans bromides there. You actually get a little bit of the cis as well. It's not, there's some ideas for why that happens, but it's not real sure. So you get a mix. The trans is major. And then if you add, so this is one equivalent of Br2, same deal here. If you add a second, then you get 4 bromides on there. That's not a real common reaction. Right, you can do that with Cl2 as well. Molecules that have 4 bromides on adjacent carbons are not real common in nature. I don't know if there's any in nature. Anyway, you're not going to see a lot of that. But the mechanism for the Br2 basically follows what you see in the alkene. The mechanism's a little more complicated. Oh, sorry.
If you didn't write one equivalent, you just wrote like HBr, would you go all the way to the alkane or
So, yes, let me put up some speeds here. So this is relative in the reactions. This is fast. This is fast. This is slow. And this is slow. Right? So you can stop in the middle. So long as the first step is fast and the second step slow, you can stop in the middle. If they were flipped around, if this first step was slow relative to the second step, you'd only be able to isolate that final product. To your question, if I don't give you stoichiometry, then, and this is, again, this is my own personal point of view. If I don't give you stoichiometry, you can basically just put either one of them down. Right? If I don't specify one equivalent or excess or two equivalents, you could give me these products, you know, the intermediate step, or you could get the final. But if I do give you stoichiometry, you'd need to nail it down. The mechanism on the top one, the addition of HX to alkynes, is kind of funny. It's in the book. I'm not going to go into it much, but it's actually a trimolecular reaction. There aren't many of those. HBr in the kinetic equation, the rate law for this reaction shows up twice. And it's basically the alkynes grabbing an H at the same time as a Br is attacking the alkyne. Yeah.
For the halogenation reaction,
Uh-huh.
is the product that's the E isomer typically like?
You would typically have more of this one than that one.
Okay.
But it's going to depend on concentrations and temperatures and what the substituents are. Yeah. I wouldn't worry about it. That's what I'm saying. All right. So I think that's all but the. We've done ozonolysis. Have I done ozonolysis in here? Okay. So the other reaction in chapter 9, the other addition that alkynes do, that alkenes also do. So going back, what I mean by that is, if you guys know the chapter 8 reactions, it doesn't mean you're going to definitely know what happens in the chapter 9 reactions, but they're pretty similar, right? They at least start going down the same path. The one pretty big difference is addition of water. Okay, so let's just review. If we add water, I don't want to do a cyclohexane. So if we add water across styrene, the pi bond of styrene, all we need is H3O plus and H2O. This will go in a Markovnikov fashion. All right, and there's our addition of water. You can also do this you can do an oxymercuration. Oxymercuration also gives you Markovnikov addition. The only reason to use mercury with an alkene is to avoid cationic rearrangements. If we do the same reaction with borane, followed by alkaline peroxide, we get anti-Markovnikov addition. Okay? All right, so let's look at what happens if we do this with alkynes. So the first thing you're going to see with an alkyne is you have to use mercury. Right, so you can't add water across a carbon-carbon triple bond without including catalytic mercury 2. And again, this is one of those, this is what Klein tells you, this is what people knew in the 1960s. Today you can use gold, there's a whole host of transition metals you can use in this reaction. But we're going to stick with mercury. So if you end up, you know, an organic chemist, dig into the literature, there's better ways of doing this than mercury today. But the principle basically holds. Yeah.
Is that a wedge on that edge?
No, that's just a bad line. All right, so predict what the product would be there on the addition to alkyne. Okay, so what I would expect you drew, Markovnikov addition of water, would be that. Maybe you added it twice. Which would be that. Either one of those would be pretty logical extrapolations of chapter 8. The product is that. And they're all three of those structures are related to each other, right? In a way that is a really nice segue to chapter, or not chapter 2, to Orgo 2. We have some names for this. So this is going to be the keto form. It turns out that this is actually a ketone. The product here is a ketone. Carbon-oxygen double bond. The carbon's bonded to 2 carbons. But the keto form, any of the functional groups that you look at, so any functional group that has a carbon-oxygen double bond, a carbonyl, will have a keto form, an enol form, and a hydrate form. Okay, so the keto form has the carbon-oxygen double bond. The hydrate form structure is going to be exactly the same, but instead of that carbon having a double bond to oxygen, it's going to have 2 single bonds to oxygen. The hydrate comes just by adding water across this carbon-oxygen pi bond, right? So over here, we're adding water across the carbon-carbon double bond, so an H on one carbon, OH on the other. In the carbonyl, we add an H to the O and an OH to the C. That gets you a hydrate. And then we also have the enol form. And that's going to look like that. And you get enol from alkene, ol, right? So an enol. These are all equilibria. And usually the keto form is highly favored. Not always. We'll talk about a couple of examples. But you guys will see this in biochemistry. There's a lot of this in, well, I guess the best example is probably in the DNA bases, DNA and RNA bases. There's quite a few of those molecules that have keto-enol tautomerization possibilities and exist more as the enol for reasons that I'll explain here in a minute. Okay, so in this mechanism, I'm not going to ask you guys to use the mercury at all. I feel I don't like this very much, but the mercury really complicates the mechanism. I'm going to keep saying it's vital. Like, this reaction doesn't work if you don't put the mercury in. But I'm going to draw it as, I'm going to go through this mechanism as if it's just a simple protonation and water attack. So pi bond attacks the H3O plus. And here's the problem with this is why you need mercury. Right, so we add the H on there. I mean, there's another H there. So that cation is terrible. Right? Cations on sp2 carbon, or actually it's an sp carbon. So cations on a double bonded carbon are extremely unstable and basically really can't form. It's why this HBr addition isn't a simple Markovnikov addition where you make a cation. The Br2, you make the bromonium ion. You don't make a vinyl cation. So down here, when you protonate an alkene, you get an sp2 cation. That's okay. Here you get an sp cation, and that's really bad. All right, so the mercury comes in here, and when the pi bond attacks the mercury, you get that oxymercury, or you get that mercurinium ion, and then water attacks that. But you have to lose the mercury as well. It's a little easier to see how this works by going through the vinyl cation. Okay, Now water is going to attack that. And again, I can't emphasize this enough. Looking at the mechanisms you turned in yesterday, a lot of you are still like water will attack, but you just have OH come in. So you lose a step there. So this equilibrium water comes in. Water is if water attacks a cation, both of those hydrogens come with it. Now water will take, and then water can take that proton. So it's a two-step process. Having water attack an electrophile to become an OH takes two steps. You can't do that in one step. You can't even, some people like to have an arrow where something's grabbing the H off the water at the same time the oxygen's attacking. That's not how that works. This has to be two distinct steps. All right, and then this gets us the enol. And that's what you would think would be the product, right? That's the rational extrapolating from chapter 8 Markovnikov product for addition of water across an alkyne. So how do we go from the enol to the ketone? So this is the question now. How do we go to there under acidic conditions? Go ahead and try to see if you can do that. Draw a mechanism to go from the enol to the ketone. It is two steps. Okay, so again, this is our conditions. We've got some mercury in there, but you don't need the mercury for this. And this happens, this equilibrium, by the way, that I've put on the board, the enol hydrate in keto forms, if you have a carbonyl compound in water, you will always have all three of those. Usually there will be a lot of the keto form, there'll be a trace of the hydrate and enol. And when I say trace, I mean the equilibrium constant here is if you have one hydrate, you may have 7 or 8 enols, and you'll have, I don't know, 1 trillion, 10 trillion keto forms. All right, for a given carbonyl compound. I'll talk about some exceptions here in just a second. Okay, so the first step here is going to be protonation of the pi bond. Again, if you're protonating the pi bond, use a strong acid. There were a couple of cases on the mechanism you guys turned in where people used basically just like methanol or water to protonate an alkene. That's going to give you a carbocation and hydroxide or methoxide. Right? That's going to, you're basically producing a really strong acid and a really strong base. And that's never going to be a productive reaction. So we're going to protonate. And again, you could protonate the OH and that would just go back up here. Right? Sorry. This is an equilibrium. So you can protonate the OH and then lose the proton on the OH and just go back to the enol. It just doesn't get you anywhere. So if you protonate the alkene, again, this is going to go to give the most stable carbocation, and this cation, right, so that blue H goes onto the end to make a methyl. You get a tertiary cation that's delocalized with the benzene ring, and that OH has lone pairs that can stabilize it, right? So you could draw a resonance structure here, where the positive's on the O, and there's a carbonyl there, carbon-oxygen double bond. All right, from there, the last step is water taking the OH proton, the OH electrons swing down and make the carbon-oxygen double bond. Again, you could have drawn a resonance structure for the cation where the positive is on the O and there's a carbon-oxygen double bond already there. And now the base is just coming in and taking the H off the O and neutralizing the charge. So that's fine. And then this gives us this is an equilibrium. This is an equilibrium. All right, so 2 steps. Going from the enol to the ketone, protonate the double bond, get a cation on the carbon bonded to the oxygen, then lose the proton on the oxygen, make a double bond. And you might be wondering, like, you could also do here, the water could instead add into the cation, and in 2 steps, that would take you to the hydrate. All right, so you can see there how the hydrate and the enol and the keto form are all sort of interchangeable. Okay. So like I said, almost always the keto form is going to dominate. An example of where this doesn't work is here. So this would be the keto form. Draw the enol form of that green ketone. Okay, so the requirement to get an enol, the atom bonded to the carbonyl has to have 1 H on it, at least 1 H. All right, and this carbon does. So you could move this hydrogen up to the O and put the double bond there. But then you'd have accumulated double bonds. You'd have an sp carbon, which is linear, in a ring. So that's not going to work out. So the only good place to take that H is from this carbon. And so the way this is going to work, and again, the mechanism is going to go just like I've drawn down here. You can do keto-enol tautomerization either under acidic conditions or basic conditions. We're going to see base here in a minute. but you're gonna take the H on the atom bonded to the carbonyl, that H will move to the O, the double bond will move here. Again, that's not the mechanism, I'm just saying what you have to do. All right, so this compound, this is the enol. And here, like I said, usually the keto form is heavily favored. In this case, the enol form is the only one that you find. The reason for this, so this is called, you've actually seen this, phenol. It used to be the active ingredient in Lysol. It's really toxic. Right, so you'd spray Lysol everywhere to sterilize things. Distracting myself, sorry. Okay, so the reason the enol form here is so heavily favored is this ring is aromatic, this ring is not. So this is something, this ties to other molecules I've drawn on the board. And it's really hard to explain without taking a fairly deep dive into molecular orbital theory, which, it's November 17th. You have an exam next week. None of us want to take a dive into anything right now. So, on the board, like this is a 6-membered ring, there's some double bonds in it. That ring is not aromatic. I've said this in class a few times. These benzene rings are much more stable than Lewis structure would suggest. Lewis structure alone would suggest. I mean, one thing you can tell, they're all 6 atoms are sp2 hybridized. They're in a hexagon. The geometric bond angle for a hexagon is 120 degrees. The desired bond angle for an sp2 carbon is 120 degrees. That's a nice match. It's a coincidence, but it's a nice match. There are quantum mechanical reasons, like I said, molecular orbital theory, that having a ring where every atom in it is participating in the pi system, right? So every atom in this ring is sp2 hybridized. That means it's got one p orbital that's participating in all the double bonds. If you have a certain number of electrons, 6 is one of those numbers, the ring gets this, it's almost noble gas-like stability. It's not. That's a bad analogy, but for right now, until you take Orgo 2, that's what you ought to think about it. So over here, this ring is not aromatic because that carbon right there with the H is sp3 hybridized, so it's not participating in the pi system. So like I said, if you make the ring aromatic, you get this kind of special quantum mechanical stabilization, and that's enough to make the equilibrium constant for that equilibrium like 10 to the 20th. I mean, basically there's none of the left molecule at all. Okay? One second. You're going to tell me about the camera? Or?
Yeah,
Okay.
that and a question.
Okay. So if you look at all these reactions we're doing from chapter 8 and 9, benzenes don't do them. Like I said, this is not noble gas. Benzenes do chemistry. Do. Benzenes will do chemistry. You will spend like 6-7 weeks next spring looking at the chemistry of benzenes. Probably not that long. If it was my class, it would be that long because it's a flat molecule. You don't have to worry about chiral centers. That's what I did my PhD on. So we would talk about this a lot. Anyway, in these reactions in chapter 8 and 9, ozenolysis